Have you ever really stopped to think about it? How can a machine that only gets on and off do, well, everything? From spreadsheets to crazy complex video games. It seems impossible, right? Well, that's exactly the mystery we're going to unravel today.
So yeah, how does a computer think using just on and off? It feels like it shouldn't work. But the whole secret, the answer to this massive question, it actually starts with something incredibly small and brilliant. All right, so let me introduce you to the hero of our story, the transistor. It's really just a tiny electronic switch. The best way to picture it is like a gatekeeper for electricity. It's got this part called the base. If you send a little bit of current to that base, boom, the gate swings open and a much bigger current can flow right through. But if there's no current at the base, the gate stays firmly shut. Simple as that. And that right there, that's the whole game. No current on the base means the transistor is off. It's basically an insulator. We call that state a zero. But when you apply that current, it flips on, becoming a conductor, and we call that, you guessed it, a 1. That's literally it, zeros and ones. Every single thing your computer does, from the mundane to the mind-blowing, is built on this simple, two-state foundation. Okay, so what can you do with just one of these things? Turns out you can build the most basic piece of logic there is, a NOT gate. You might also hear it called an inverter. It's this super clever but simple circuit that just flips the input. You feed it a 1, it gives you a 0. You feed it a 0, you get a 1 back. Simple, right? But believe me, this little trick is incredibly useful.
So yeah, one transistor is cool and all, but the real power, the magic of computing, that happens when you start combining them.
So let's do it. Let's see what happens. What we're building here is called an AND gate. See how the two transistors are wired up in a line, one right after the other? Think about it. For electricity to make it all the way from start to finish, what has to happen? Well, the first gate has to be open, and the second gate has to be open. If either one is closed, the path is broken. No current flows. So the key takeaway here is you only get a 1 at the output if input A and input B are both 1.
Okay, you can probably see where this is going. Imagine trying to draw a circuit with millions of these things. It would get messy and super complicated, like immediately. There has to be a simpler way to think about this, right?
Oh, yes, there is. And honestly, it might be the single most important idea in all of computer science. It's called abstraction. It's basically the art of hiding complexity. You take all that messy, nitty-gritty detail, the transistors, the wires, and you package it all up into a nice, simple, reusable block that just works. All you need to know are the rules. And just look at the difference this makes. Before, you've got this complicated diagram of two transistors hooked together. But after abstraction, you just have this one clean symbol for an AND gate. We don't have to think about the transistors inside ever again. We just know the rule. If A and B are 1, the output is 1. So much easier. And now that we have this idea, we can create a whole toolbox of these logical building blocks. We've got our AND gate, sure, but we can also build an OR gate. That's one where you get a 1 if at least one of the inputs is 1. Or an XOR gate, which is a bit special. It only gives you a 1 if the inputs are different. So now we've got this set of tools, and with these, we can build something truly amazing. Okay, so we've got logic down. True, false, and, or, that's great. But how in the world do you get from these simple decisions to actual math? How can a bunch of gates possibly add two numbers together? Well, first, let's just go over the basic rules of adding in binary. It's mostly what you'd expect. 0 plus 0 is 0. 1 plus 0 is 1. But what about 1 plus 1? In our world, that's 2. In binary, the number 2 is written as 1, 0. And this is the key insight. That 1 plus 1 operation actually gives us two different outputs. The sum is 0, and we have a carry of 1. Just like when you carry the 1 in regular addition.
Okay, now let's think back to our logic gates. For that sum output, we need a gate that gives us a 1 only when the inputs are different. Does that ring a bell? That's an XOR gate. That's exactly its job. And for the carry output, we need a 1 only when both inputs are 1. Hey, that's our AND gate. So look at that. You combine an XOR gate and an AND gate, and you've just built a circuit that can add. How cool is that?
This is awesome. It really is. But we've hit a problem. This little circuit, it's called a half adder, and it's great for the first column of numbers. But what about the next column? What happens when we have a carry coming in from the previous calculation? Our circuit only has 2 inputs. It can't handle a third. And the solution is the full adder. Now, it's a bit more complex under the hood, but its job is beautifully simple. It takes 3 inputs,
Input A, input B, and that carry-in from the last column. It's the whole shebang, the complete package for handling one column of addition.
And here's where things just get ridiculously powerful. You want to add two 8-bit numbers? Easy. You just chain 8 of these full adders together in a line. The carryout from the first one becomes the carry-in for the second, and so on down the line. And because electricity moves at, basically the speed of light, this whole calculation happens almost instantly. But hang on, what if the answer is too big? What if it doesn't fit in those 8 bits? That's what that final carryout signal is for. It's called an overflow flag, and ignoring it can have, well, catastrophic consequences. I mean, the source material brings up the Ariane 5 rocket explosion in 1996. That was a billion-dollar disaster caused by a software error and arithmetic overflow. So yeah, these tiny, low-level details, they matter a lot.
Okay, so we've figured out how to build circuits that can add, and you can imagine how we could build others to subtract or do other kinds of math. But that brings up a new question. How does the computer choose which math to do? How does a line of software code actually tell the physical hardware what its job is for this specific instruction?
The secret is hidden inside the machine instruction itself, in a little piece called the opcode. That stands for operation code. It's just a sequence of bits that works like a command. For instance, maybe the computer agrees that 00 means add and 01 means subtract. It's the direct language that the hardware is built to understand.
So how does the hardware read that command? For that, it uses another clever circuit called a binary decoder. It's pretty simple, actually. You give it a binary number, say 01. The decoder looks at that, knows it's the number 1, and then it does one thing. It turns on only the output wire at position 1. All the other output wires stay off. It's basically a selector switch.
Okay, let's put it all together now inside what's called the Arithmetic Logic Unit, or the ALU. This is basically the mathematical brain of the computer. Here's what happens. The opcode from the instruction gets sent to the decoder. The decoder then activates one, and only one, output line. And that single active line works like a switch. It selects which result. The one from our adder circuit, or maybe one from a subtractor circuit, is the one that gets passed along as the final answer. It's the bridge. It's how the software instruction tells the hardware which tool to pick up and use. And this whole chain of events, from top to bottom, it just brilliantly illustrates the incredible power of abstraction. I mean, just think about the journey we just took. We started with a single dumb transistor that could only be on or off. Then we bundled those up, abstracted them into logic gates that can make basic decisions. Then we used those to build adders that could actually do math. And finally, we put it all together into an ALU that can read instructions and choose the right calculation to perform. Each new layer completely hides the messy details of the one below it. It's how we build something so unbelievably complex from the simplest possible part.
So there you have it. We've built a little brain. A brain that can calculate and make decisions based on instructions. It's an incredible achievement, really. But take a look at our model. It can calculate, sure, but what's the one crucial thing it's still missing?